we now want to consider momentum, the behavior of the momentum on this same system. So we got slope 1, slope 2. I haven't labeled it here, but it's the same system we did in the preceding 2 summary videos. And I would ask you to sketch the momentum vectors just before and after the point B, and that should be plural momentum vectors. The momentum vector before collision would be P1, and it's going to be parallel to the first ramp, and P2, the momentum after passing the point B, parallel to the second ramp. I probably exaggerated these angles a bit, but here's P1, here's P2. I then ask you to sketch the components. The component P1 perpendicular, the component of P1 perpendicular to P2, of P1 perpendicular to the second incline. Okay, well, the second incline has the direction of P2, so that if we sketch the perpendicular vector, the component of P1 perpendicular to P2, we're sketching the vector, the component of P1 perpendicular to the incline, P2 being in the direction of the incline. Okay, so, well, to sketch the component of P1 perpendicular to the incline, we first project P1 onto P2. Okay, that gives us the vector P1 parallel. That can be subtracted from P1 to get P1 perpendicular. Of course, just sketching it, we can just sketch a dotted line perpendicular to P2 and project P1 onto that dotted line. So you want to be able to think about it both ways. One of those ways is going to be more valuable to you in a multivariable situation, multivariable calculus type situation. Okay, well, but there are the components. Now, question is, what happens to these components when the ball makes the transition from the first ramp to the second? Well, the perpendicular component of the P1 momentum, of the ball's momentum before the transition point, is perpendicular to this ramp. Okay, and anything perpendicular to this ramp, any momentum perpendicular to this ramp, is going to be lost when the ball hits the ramp. If you hit something perpendicular, you either bounce back or just lose your momentum, assuming the thing you hit is massive enough to withstand that, and the ramp supported by the table is plenty massive to get rid of the perpendicular component of the momentum of this ball. So that component goes away. Now, kind of ignoring the question, what happens? Well, what if it rebounds a little bit? That's not going to be very relevant to this situation. Okay, so you lose the perpendicular component of the momentum, and that leaves only the parallel component of the momentum. So let's do this for slope, for some specific slopes. Slope 1 is 0.12, slope 2 is 0.08. Now, in a minute, I'll do another video where we just analyze this from the point of view of the slopes, but your natural reflex is you're going to want the degrees, because you can use the degrees to quickly calculate the components of P1. And that's what we're going to do, okay? Because we want to ask what percent of the momentum is lost at the point B. Now, right now what we know is all the momentum perpendicular to the second ramp is going to be lost at point B. We don't know what percent that would be of the total momentum, and we've got to be careful about that. So let's redo this sketch. We've done that up here. We got P1, we've got P2. Now, it took way too long for people to figure out what the angle between these two vectors would be. I've got it written here, it's 12 degrees, but I was getting 168 degrees and 7 degrees and a bunch of different stuff. To figure this out, if this is 7 degrees and this is 5 degrees, well, we extend this a little bit, and we have this angle being the alternate interior angle, with this one being 7 degrees. 7 degrees and 5 degrees gives us 12 degrees. Okay? And that's basic early high school geometry. So you want to be able to use that kind of reasoning. And I'm not too surprised that you didn't do that. You could have if you'd have put yourself into that mindset. You've got to carry that mindset along with you. You've got to remember your very basic algebra and geometry. You do well with the algebra. I'm still questioning how geometry is even taught in the high schools, but that's a reasoning that you simply have to be able to make. That's a jump you simply have to be able to make. So if you got to review a little bit of basic geometry, might not be a bad idea if you had trouble doing that and relating it to this situation. There are plenty of cases in this course where you need to be able to make geometric arguments and see the geometric relationships. So in any case, if you do that, you're going to then be able to project P1 onto P2 knowing this angle. So P1 parallel is going to be P1 times the cosine of the angle, and P1 perpendicular will be P1 times the sine of that angle, that 12 degrees. Well, I didn't use the angle, I just used what I know about slopes and what I'm going to explain in another video where we go out into some of the ways of seeing things that you probably need to develop a little more. In any case, if you use the 12 degrees to calculate this projection, or if you use some other method, you've got the angle here. Here's the picture. This angle is now 12 degrees, so clearly it's going to be P1 times the cosine of 12 degrees, P1 times the sine of 12 degrees. You get that P1 perpendicular is approximately equal to 0.2 P1. Now I got that just by adding these slopes and using a small slope approximation. And remember, this is the magnitude of P1 perpendicular. I'm not worried about positive or negative right now. That tells us that P1 parallel, by the Pythagorean theorem, it's going to be 1 minus 0.2 squared times P1, and you should think through how the Pythagorean theorem gives you that, and that's 0.98. Now that's an easy calculation. 0.2 squared is 0.04. 1 minus 0.04 is 0.96, and the square root of 0.96 is twice as close to 1 as 0.96 is. So the square root is going to be 0.98. Again, a small number approximation that's very good with these numbers. Okay, so if you went through all the trigonometry and everything and did all the calculations, you would come out with this result, and you should go through those calculations, but you should be able to do this in an approximation without using all those calculations as well.